Good morning, students. So after the first video which tells us the syllabus of class 10th maths, here we are with the second video which will start with first chapter, that is real numbers in class 10th. Real numbers. So in class 9, under the topic real numbers, we have studied about irrational numbers, rational numbers, their definition, their examples to show irrational numbers on a number line, to show decimal expansion of rational numbers on a number line, and to find irrational numbers between two given rational numbers, to find irrational numbers between two rational numbers, and the operation on irrational numbers, and then some laws of exponents we have done in class 9th. But here in class 10th, we will be going with four topics under the rational numbers. And the very first topic that we will be doing here in this class 10th under this topic is Euclid's division lemma. And second topic here in this chapter we'll be doing is fundamental theorem of arithmetic. Third topic here we'll be doing is to prove like under 2 is an irrational number. In class 9, you have shown under 2 on a number line, you have shown irrational numbers on a number line, but here we will be proving that these are irrational numbers. And the fourth topic that I am doing here in this chapter is decimal expansion of rational numbers. In class 9, you have studied rational numbers, their decimal expansion. Let us remind what was the decimal expansion of a rational number. It was either terminating or non-terminating. So here in this chapter again we will be discussing the decimal expansion of rational numbers, which is terminating or non-terminating, just by observing the denominator or the factorization or the factors of denominators will tell us whether it is a terminating or non-terminating. Then let us move back to our very first topic, that is Euclid's division lemma. So with this, you will also be preparing your notes. In your notebook, just write down chapter name, that is real number, chapter number is 1. These are the four topics that you will be writing. And under the heading of Euclid division lemma, you will be writing this. Before moving to the statement of Euclid division lemma, let us recall what we have done in our junior classes. In our junior classes, when you used to divide a number by another number, we used to write it like this. Suppose I am dividing this 14 by 2. So what I get a quotient as 7 and a remainder as 0. And the same thing, when we used to verify whether we have done this correct or not, to verify what we used to do, we used to write it like this in the form dividend equals divisor into quotient plus remainder. Here what is our dividend? Dividend is 14, divisor is 2, quotient is 7, and our remainder here is. So now let us again change our dividend. Let us change it to 15. Our divisor remains same, quotient is also same, but our remainder changes. Remainder becomes 1. So this can also be written in the form 15 equals 2 into 7 plus 1. So this is one of the examples Now let us change our dividend as well as divisor, and let us see what changes we get in our remainder. Let us change the dividend to 18, divisor to 3, and our quotient becomes 6, remainder is 0. Now let us write the same thing in this form. It's as 18 equals 3 into 6 plus 0. Again, changing our dividend to 19. Quotient divisor remains same. Quotient remains same, but our remainder changes. So it's 19 equals 3 into 6 plus 1. Then let us move to 20. 3, 6 are 18. 2 is our remainder. When you change it to 20, it is 3, 6 are 18 plus 2 is our remainder. Let us move to the dividend 21. So, what changed? We got in our quotient and remainder. Quotient becomes 7 and remainder becomes 0. So, what we see here that remainder has started repeating. If I change this dividend to 22, our remainder will be 1. 23, remainder will be 2. So, as soon as you change the dividend, our remainder keeps on changing. But it is restricted to 0, 1, 2 when the divisor is 0. When you see here, when the divisor was 2, our remainder is 0 and 1. Now, as soon as you change your dividend to 16, again our remainder is 0. You can see it has started repeating. Now, what happens when our divisor is 4? Then let us go with an example. Let us take our dividend as 20. Divisor is 4. 4 5s are 20. Our remainder becomes 0. 4, if our dividend is 21, 4 5s are 20, remainder is 1. 22, 4 5s are 20, remainder is 2. 23, 4 5s are 20, remainder is 3. Then again, if our remainder, if our divisor dividend changes to 24, 4 6 are 24, remainder is 0. Now again, let us put the like in this format. Our dividend was 20, divisor is 4 5s are 20 plus 0. 21, 4 5s are 20 plus 1. 22, 4 5s are 20 plus 2. 23, 4 5s are 20 plus 3. 24, 4 5s are 4 6s are 24 plus remainder is 0. Now you see that it has again started repeating. If I take this as 25, it becomes 4 6 are 24 plus 1. 0 1 2 3. 0 1 2 3. It keeps on repeating as soon as our divisor changes to 4. So what we observe here as is a pattern which clearly tells us that the remainder cannot be equal to or greater than the divisor, but it is again greater than equal to 0. So we see here that remainder is 0 and 1. Here you have seen that remainder is 0, 1 and 2. Here you have seen that remainder is 0, 1, 2 and 3. When our divisor here was 2, when our divisor here was 3, when our divisor here was 4. So understood? Now let me give you the definition of Euclid's division lemma. It states that given two positive integers a and b, there exists a unique integers q and r satisfying a equals bq plus r, where you have understood with the examples that this remainder is less than the divisor b but greater than equal to 0. I repeat the statement which is given in on page 3 of your book, Euclid division lemma. It states that given two positive integers a and b, there exist unique integers q and r satisfying this condition a equals bq plus r such that r is less than b but greater than equal to 0. So taking this example, in this example if b is 2, our remainder r is what? 0 and 1. In this example if you see b is 3, b is 3, then our remainder is 0, 1, 2. Here, if b is 4, then our remainder is 0, 1, 2, and 3. So this is what Euclid's division lemma says. Using this Euclid division lemma, we have an application in which we used to find the HCF of two numbers. That we'll do later on. Let us understand it in a proper way with some examples. We'll go with some questions based on this Euclid division lemma. Then we'll move to fundamental theorem of arithmetic and to prove and root 2 is a rational number, decimal expansion of rational numbers. Let us go with some examples. So for preparing your notes, you may note down this thing. Under the first topic, Euclid division lemma, you may note down first this example with these calculations. This thing you will write, and then you will write this using these. You will write on the right side of this page, and then this example you will write on the right side of the page. You will do these calculations, and then later on you will write under these things. The remainder is 0, 1, 0, 1, 2, 0, 1, 2, 3, and then you will write down the definition of Euclid's division lemma under these examples. Under these examples, after doing this, you will write out Euclid's division lemma, that is its statement, and then its mathematical form. This is its mathematical. So simultaneously you will be preparing your notes also on your fair notebooks. Now let us move to certain examples based on this Euclid division lemma. Using this Euclid division lemma, we can tell, or we can state, or we can say the different forms, even or odd form of a positive integer. We already know what is an even integer, what is an odd integer. Our even integer, we can write 2, 4, 6, 8. These are even integers. 3, 5, 1, 7, 9, so on. These are odd integers. But when we do Euclid division lemma, under this, if you want to write even integers, it have different forms. When we take b as one value, and according to that, you can say what is even integer, what is odd integer. Now, if I say 2 is an even integer, yes, it is even integer. Now, if I multiply it with any number, say for example q, it is again an even integer. So, taking example, you multiply 2 with 3, it is 6. 2 with 4, it is 8. 2 with 5, it is 10. So, you can see that whenever you multiply any integer with 2, you are again going to get a even integer. But what if you do it like this? If I multiply 2 with 3, I get 6. When I add 1 in it, it becomes odd. 2 into 5, when you add 1 in it, it becomes 11, which is again odd. So, given a general form to this pattern, I can say that 2q is even integer. I can say that 2q plus 1 is odd integer. Understood? So, if we change b, what happens then? Let us write some examples based on this form. There is a question. It says that question 1 you will note down on your notebook. Question 1, which is show that any positive even integer is of the form 2q plus 1, where q is some positive integer, where q is some positive integer. So using Euclid division lemma, we will solve it. How to write answer to this question, which will fetch you full marks in board exams, is let A be any positive integer. Let A be any positive integer and B equals to 2. Now if A is any positive integer and B is equal to 2, then by Euclid's division lemma, using this lemma, sorry, then by Euclid division lemma, what can we write in that form? We can write A equals BQ plus R, where R is less than B but greater than or equal to 0. Putting the values of B here as 2, here we can write here A equals 2Q plus R, where R is what? R is equal to 0 and 1 here because B is 2. So we have different forms of A, that is A equals 2Q plus 0. Remainder A equals 2Q plus 1, which are its two forms. So you can see, as we have already discussed, that whenever you multiply any integer with 2, it gives us a even integer. This is an even one. And you are adding nothing to it, you are adding 0 to it. It remains even. The same thing, this is an even. When you are adding 1 to it, it becomes odd. So here completes our answer, that any positive even integer is of the form 2q. Any positive even integer is of the form 2q. And any positive odd integer is of the form 2q plus 1. So these are its two forms using Euclid division lemma. So we have proved that this is an even number, this is an odd number. So you can note down in your notebook. This is its answer. Let us move to another question. Now, not only 2q is an even integer, if I take b as a 4, there are other forms also which are even. So what he says in the next question, question number 2, show that any positive even integer is either of the form. Let me restate the question. Is either of the form 4q, is either of the form 4q or 4q plus 2, and that any positive odd integer is again either of the form, is either of the form 4q, is either of the form 4q plus 1 or 4q plus 3, where q is again some positive. Now let us prove this using Euclid division lemma. Answer to this question is, let A be any positive integer. Let A be any positive integer. Let A be any positive integer and B. This time what we keep B as? We keep B as, yes, 4. Let B equals to 4. Then by Euclid's division lemma. Then by Euclid's division lemma, we can write A as BQ plus R, where R is less than B but greater than or equal to 0. 0. Here the value of b is 4, so we can write 4q plus r, where r is having values what? 0, 1, 2, 3. So I have 4 different values. So we get 4 different numbers. That is a equals 4q plus 0. A equals 4q plus 1. A equals 4q plus 2. A equals 4q plus 3. So these are the 4 different forms of any positive integer. These are the 4 different forms, in which you can well imagine yourself that this form, when you multiply any integer by 4, it is an even number. When you are adding 0 to it, it remains even. You can write that this is an even number. We are adding 1 to it or 3 to it, it becomes odd. This is also odd. When you are adding 2 to it, it remains again even. So this is the completion of this question also. Now again there is one more question which is there in your book, that is to show that any positive integer is either of the form. When you change b to 6, it becomes what? 6q. 6q plus 2 or 6q plus 4. And any positive odd integer is either of the form what? 6q plus 1, 6q plus 3 and 6q plus 5. Let me restate the question. You can note down this. Now let me restate the question again. Show that any positive even integer is either of the form is either of the form 6q or 6q plus 2 or 6q plus 4, and that every positive odd, better to write positive the complete word than to write its short form, positive odd integer is either of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some positive integer. Now let us solve this question. Again, the same steps you will follow. Steps, I focus on this steps because we have some term here to define. We will do it later on. That is algorithm. We will define it later. That is also given in your book. So let us solve this. Let A, we will have the same steps. Let A be any positive integer. When A is any positive integer, and this time B equals what? And this time B is 6 and B equal to 6. Then by Euclid's division lemma. What we have? We have A equals BQ plus R, where R is less than B but greater than equal to 0. Here the value of B is 6. So we will write this as 6q plus R, where R can take values what? 0, 1, 2, 3, 4 and 5. Because we know that our remainder is 1 less than our divisor and but greater than equal to 0. So it has 6 different values. So the form of A. So any positive integer A can be written in these 6 different forms. That is 6q plus 0, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4 and 6q plus 5. So you already know the answer. Which one are even, which one are odd? This is an even number because when you multiply any number with an even, it becomes even. So you may write even, you may write odd, you may write even, you may write odd, you may write again even, you may write odd here. So this proves our answer that 6q plus 2, 6q plus 4 are even integers and 6q plus 1, 6q plus 3 or 6q plus 5 are odd integers. Other than this, apart from this, at the end or note you may write down because we know that when we multiply any integer with 6, when we multiply any integer q, any integer you can write any integer q with 6, we get even integer. We get even integer. And if you add 1, 3 and 5 in it and adding say let us go with the even one first. 6q is even, 6q plus 2, 6q plus 4 and adding 2 or 4 in it, it remains even integer. But adding 1, 3 or 5 in it, but adding 1, 3 or 5 in it, it becomes odd integer. This statement you can write in previous two questions also. This was the third one. This was your third question. The previous two questions also you can write down these statements. So this was the questions based on Euclid division lemma. In the next class we will be studying how to find HCF of two integers using Euclid division algorithm. Now first, sorry, let me define